G'day YouTube, Warbles on a lot here. Let's deal with Newton versus Bernoulli. When I was young, but a child dreaming of aeroplanes that I one day wanted to build, the issue of how wings generate lift was taken to be something of a done deal. Ever since the Wright brothers used a simple homemade wind tunnel, it has been widely understood that a curved aerofoil produces more lift and less drag than does a flat plate surface, although Lawrence Hargrave had established that well before the Wright brothers. The accepted theory, according to Boyle, Bernoulli, Coanda and Venturi, is that two molecules of air moving from point A1 and B1 to points A2 and B2 must traverse a different distance. It's shorter along the bottom than it is along the top. And it was traditionally believed, it was held, it was asserted, it was assumed that these two molecules of air here must always arrive at the trailing edge simultaneously. And therefore, it was always assumed that the air going over the top of the wing must increase in speed. And as I said, according to Boyle, Bernoulli, Venturi and Coanda, as the air increases in speed, it reduces in pressure. And therefore, it was expected that if somebody took an aerofoil and measured the pressure above it and measured the pressure below it, they would find a pressure differential. This can be done with a flat plate, and it'll generate a reaction force, which can be resolved into a vector diagram, which is dependent on airspeed and the angle of attack, which changes the proportions of the vector diagram. It has long been known that a flat plate will generate lift, but it will also generate a lot of drag. Particularly a lot of drag compared to a curved aerofoil with a blunt leading edge and a sharp trailing edge. This says upwash, increased velocity of airflow, decreased velocity of airflow, downwash. And we see that the entire air mass has been deflected down, just as it has with the flat plate. And it was traditionally held that the downwash was the cause of the drag, which lift incurred as the wing moved through the air. Very early on, they developed picturesque apparatus to test this varying pressure theory. Vent ports labelled H at the front, A, B, C, D, E, F, G, K, L, M, N, O, P, top and bottom on the wing. We have a fluid reservoir, an adjustable reservoir. We have the datum line to which all the glass tubes were filled. We have a static port on either end, and we have the vent ports A, B, C, D, E, F, G, H, K, L, M, N, O, P along the top. And when air is passed over and below the aerofoil, we find a suction at A, B, C, D, E, F, and G. At H, on the leading edge, there's a high pressure zone. There's a high pressure zone under the wing. And this apparatus allowed diagrams such as this to be drawn. And the assertion had been for 70 odd years that this high pressure area here and this low pressure zone here were responsible for the wing sucking itself into the sky, all acting through an area known as the centre of pressure. And this is what you'll find in any textbook from the end of the First World War, or pretty much up until the fall of the Berlin Wall. This is actually a 4th edition of a 1932 textbook. Now, this centre of pressure is dependent on the angle of attack of the aerofoil's chord line to the impinging airflow, such that -4 degrees, 0 degrees, +4 degrees, 8 degrees, 12 degrees, 16 degrees, and 20 degrees angle of attack. And if the angle of attack is too great, even the curved surface will stall and generate a lot of turbulence. The stalling angle is generally around 15 degrees, although with a few tricks, aerodynamicists can get up to about 17 degrees. That's the amount of change in direction that the airflow makes before it breaks away from the surface of the wing in this case, or any shape it's actually trying to follow, according to Coanda. And as a general rule, the closer an aerofoil is to a flat plate, then the lower the angle at which it stalls. High lift aerofoils are also known as low speed aerofoils, and they have big, thick, fat, blunt leading edges. The more lift an aerofoil makes, the more drag it makes, and the lower the speed that it will fly at. High lift is high drag. If you want your aerofoil to fly slowly enough for foot launching, not only will you give it a thick leading edge, you might leave some of the lower surface off behind the rear spar to act as a permanent turbulence generator, so the aerofoil behaves as if it's got flaps permanently set, generating drag to slow it down. Here we see the leading edge of the aerofoil designed by Irv Culver for Volmer Jensen for the VJ24W Sun Fun. This used to have foam styrene, 1.5mm thick, on the leading edge, as you can see there. It was removed to be replaced with aluminium. I've dug these photos out to show you the particular leading edge section, because an awful lot on the performance of a wing depends on the exact particular shape and thickness of its leading edge, because it turns out that it's the particular shape of the leading edge which determines how far away from and above the upper surface of the wing the airflow is induced to travel, because that's actually what goes on. It was discovered that nobody could quite shut up the Newtonians, who kept maintaining that it's not Bernoulli and his high and low pressure zones that makes a wing lift. It's the action-reaction consequence of generating the downflow. And eventually somebody thought to stick micro smoke generators at point A1 and B1, and lo and behold, it was discovered that the airflow going over the top of the wing does not actually increase in speed, and when molecule B1 arrives at B2, molecule A1 has not actually arrived at position A2, it's still up about here. They found what goes on is the air is deflected up by the leading edge of the wing. The air in here does in fact lower its pressure and become a partial vacuum, and that's what actually sucks the airflow back down onto the top surface of the wing. And by the time it reaches the trailing edge of the wing, it's generally stabilized and smoothed out, and the degree to which that fails results in your turbulence off the extreme trailing edge. But the resultant vector from the re-entry angle of the air coming in above the wing and the almost flat path taken by the air running under the wing results in the air being deflected down approximately half the slope of the upper surface of the wing. And even a flat plate will achieve it, although the flat plate generates a lot of drag. And the thicker the leading edge, the more likely the airflow is going to stick to the leading edge, as it comes up and over the top of the aerofoil. It's why flat plates and thin high-speed aerofoils stall at low angles and at high speeds. Considering that I was raised on Boyle, Bernoulli, Coanda and Venturi, it was a little bit of a shock to learn 10 or 15 years ago that actually they were wrong and Isaac Newton was right. It's the mass flow, the velocity of the downwash and the action-reaction of generating the downwash that makes the lift. And coincidentally, everything we thought we knew about the shape of the leading edge of the wing, controlling the performance of the wing, was all not quite right. I mean, it was empirically correct. You could use what we thought we knew to design aircraft, and the aircraft actually worked. But they weren't sucking themselves up into the sky. When the 420-pound takeoff weight VJ24W was flying, what was going on is as follows. The 36-foot wingspan with a 4-foot 4-inch chord and an 8.5-inch thickness was interacting with one chord's length of air below the wing and one chord's length of air above the wing, meaning it was effectively flying through the centre of a rectangular prism, 36 feet across and 8 feet 8 inches high. That's twice the chord multiplied by the span, gives you a frontal area of the rectangular prism of 309.6 square feet. 35 miles per hour airspeed multiplied by 1.42 gives you 49.7 feet per second, engaging 15,387.12 cubic feet of air per second, running into the front of the wing and going past it and coming off the trailing edge and being deflected downwards. As I said, the wing's 8.5 inches thick, and air has a mass of 0.09 of a pound per cubic foot, which for those of you who like strange coincidences, mark this one up. Salt water and human blood has a salinity of 0.09%. There you go. Air, seawater and blood. So that means that our 15,387.12 cubic feet of air has a mass of 1,384.84 pounds. The aeroplane only weighs 420 pounds on takeoff. So every second it flies through more than 3 times its own mass worth of air which interacts with the wing. 3.297 times the takeoff weight to be exact. So it doesn't even have to deflect that rectangular prism of air downwards by as much as 1 foot. 3.639 inches. Almost half the thickness of the wing. Boyle, Bernoulli, Coanda and Venturi got it wrong between them. Planes fly because of Sir Isaac Newton. For every action there is an equal and opposite reaction. If you take 1,384 pounds of air, fly through it at 35 miles an hour and push it all down by almost 4 inches, then your 22 horsepower ultralight motor glider is in fact a levitation machine. And I find it useful to know about all this stuff, so that, for example, when I start to play with a Chinese electric rechargeable boomerang, I can look at its specifications, notice that while it's been built in metric, it's been built to the nearest metric equivalent of an imperial measurement, half a pound a square foot of rotor area, 4-degree pitch, 5-inch advance ratio, lifts off at a downdraft velocity of 3.5 miles per hour and 5 feet per second downdraft velocity. When there's a mass flow of 5 cubic feet per second, or 0.45 of a pound per second, so the 7.712 ounce helicopter can produce 9.7697813 ounces, meaning when you take allowance for the tail rotor, changing the attitude to vector the thrust, you can draw up a significant performance chart and know what it's going to do before you try to fly it, therefore it doesn't crash. Ciao.